Hello, I'm Kushal Desai and I'm here to present LED piano keyboard. In the past few years, robotics and IoT devices are a hot topic in the technology industry. And one of the common thing in these two area of studies is embedded systems. That leads to the question, what is an embedded system? Embedded systems are a computer system which consist of a processor or a controller, a memory, and IO peripheral devices like I2C or SPI. We can mix and match between these three components and create a system with a dedicated functionality within an electrical system. Uh, some of the great examples for this embedded system or applied embedded system are Alexa, Google Dot, recent rise of drones, and the cheap drones are very, very common to have a small embedded system within them to operate certain functionalities like voices, creating of voices, recording of voices, or capturing pictures from a drone camera and stuff like that. Uh, we are today gonna explore a very, very basic project in embedded systems that allows us to understand on a very basic level what the embedded systems are. The goal of this project is to create an RGB piano that lights up an LED based on the LED strip based on what note being played on a piano. It also gives the user extra controls like enabling a low pass and high pass filter so that you can create a band pass so that you can just play at one octave and don't worry about if you went over it. Also, it allows there is an ability to pitch shift the tone from the device itself via the potentiometers that we have installed. The general layout of the project looks something like this. You can obviously change where the other stuffs are. The key components are the big LED strip on the piano keyboard, a stereo jack coming from the piano for the analog signals. The big blue device that we see is the Mbed LPC 1768, which will be our microcontroller, which also which will process this analog device coming, and then goes back and lights up the LED on the piano, as we see based on the purple wire coming out of the device. There are two more devices, the modules. This is the amplifier, the red square block, and speaker, as we can see. These are now required since we're not actually creating a piano. We're just using the piano to light up an LED. Piano usually comes with a better sound anyway. Better speakers anyway, my bad. Uh, so moving on. The general installation is provided in this document that I have created for this project, and anybody can look into it. It will provide what kind of materials needed, what kind of processors and other modules you can use to improve uh, the improve the quality of the project. The general flow of the project is that the current flow, as we speak, is the current comes from this uh, sorry, the stereo jack here. It goes to a decoupling capacitors, which is a process to eliminate the small noises that comes from the loose wire or other kind of hazards that goes through with it. That signal is rectified. The rectified signal goes to the embed, and that's being processed into the embed, and then send that that output, after the calculating what frequency it is, that output is mapped to an LED on a strip somewhere on a key. So if we press this, there should be an LED that will light up this uh, whole key. Uh, there are a couple noteworthy items on the thing that I would love to make sure that you guys understand is the aux cable usually comes with the two channels. One for the right side of speaker is the right channel, and the left side of speaker with the left channel. We just need one of the channels, so just pick one. Either one works. They pretty much have the similar signal, so you're not gonna hear a big difference from the piano. The and the second big thing is the decoupling capacitor. The decoupling capacitor's job is to cancel out small frequency that occurs due to loose wires or some other kind of hazard that happen while you are performing an experiment. This will allow us to have a stable signal which we can use for our computation. The project generally uses an online compiler, an online compiler provided by Ambit. It is free to use for everybody, so I recommend using that one. For the code, we have used an FFT uh, source file available to us, and which allowed us to go from the time domain to a frequency domain in order to get the frequency that we needed. We also used a library called Polo LED strip, which allows us to individually use an LED on the LED strip. We also wrote some code for potentiometers, which allows us to pitch shift the frequency, and also there is some more code available for the high pass and low pass filters. Moving on, the big challenges that we faced while doing this project was to determining what sample rate we should use for the fast Fourier transfer. Uh, we started with the 2 times the highest frequency possible, so we chose the max frequency that we want to play and double it for the so that we can get the Nyquist rate that we needed. But that rate that's small was not that suitable enough for the embed to do a process and send it. It was extremely slow. So we found out after a lot of experimentation and trial and error that the 10,000 samples per second gave us the best results. Even though we got some desired results, there was another big problem was that the keys were still had a one fourth of a second of a delay to LED light up after we released the key on the piano. We tried to resolve this issue using the RTOS, so the computation will happen. But since most of the stuff was sequential, RTOS didn't help us that much. It still had similar delay. Also, another big problem that we were ended up happening is we can't use more than one key at a time. Addressing 2 keys at a time is the big topic that will require a lot of knowledge in the modern physics. It goes over the idea of superpositioning 2 signals, and it's kind of hard calculation to figure out how to distinguish between the 2 keys that might be playing together, which is not doable on the current device that we are using. For that, we need a higher processing power, and so we kind of never worked on it. And that's about it for the project. Thank you so much for listening, and have a great day.